For 400 years, we have been a species of watchers. Since Galileo first pointed his glass at the heavens, every discovery, from the rings of Saturn to the glow of distant quasars, has come to us through light. But light can be blocked, it can be scattered, and it cannot tell us what happens in the heart of the most violent events in the universe. On September 14th, 2015, everything changed. We stopped just looking. We started listening. Space-time is not an empty void. It is a physical fabric. And when massive objects accelerate, they don't just move through it, they stir it. They create ripples that stretch and squeeze the very geometry of the universe. These are gravitational waves, the sound of space-time. To catch these ripples, we built the most precise ruler in human history, LIGO, the Laser Interferometer Gravitational Wave Observatory. At its heart, LIGO is deceptively simple. A laser beam is split in two, sent down two vacuum-sealed arms, each 4 kilometers long and reflected back by mirrors. If no wave passes, the beams return at the exact same time and cancel each other out. Total darkness. But if a gravitational wave passes, it performs a cosmic trick. It stretches one arm while squeezing the other. The laser beams now return out of sync. A flicker of light appears. The scale of this movement is nearly incomprehensible. A typical gravitational wave changes the length of LIGO's arms by less than 1,000th the width of a single proton. To measure this, we must filter out the vibration of the Earth, the hum of distant traffic, and even the thermal jitter of atoms in the mirrors. It is like measuring the distance to the nearest star to the precision of a human hair. How do we know it's not just a passing truck? We use a global network. By 2026, LIGO, Virgo in Italy, and Kagra in Japan work in concert. When black holes or neutron stars spiral toward their death, they emit a signature signal. We call it a chirp. As they get closer, they spin faster, and the waves become more frequent and more intense. In August 2017, we heard 2 neutron stars collide, the event known as GW 170817. Because we knew exactly where to look, we saw the flash of light follow. This was a kilonova. We confirmed that the gold in your jewelry and the platinum in our labs were forged in the fire of these specific mergers. Each collision produces several Earth masses of gold. Today, we are no longer surprised. We detect several mergers per week. We have discovered the mass gap mystery, objects like GW 230529, with masses between 2.5 and 4.5 suns. These are too heavy to be neutron stars, but too light to be any black hole we understood. We are also seeing hierarchical mergers, where black holes born from previous collisions merge again. Our ears on Earth are limited by the noise of our planet. To hear the true giants, the merging of supermassive black holes at the centers of galaxies, we must go to space. Missions like LISA will create an interferometer with arms 2.5 million kilometers long. While LIGO hears the soprano chirps of stellar mass objects, LISA will hear the baritone rumble of galaxy-shaping collisions. We are even beginning to test the Hawking area theorem. Data confirms that when black holes merge, the surface area of the new, larger black hole is always greater than the sum of the original two. We are moving from a single ear to a global, then solar system-wide, symphony. For the first time, the dark side of the universe, the 95% we cannot see with light, is speaking. The universe has been shouting for 13 billion years. We are finally learning how to hear.